Hello, honors physics students. We are ready to get started on our next topic, which is going to be circuits. Alright, so with your notes open, why don't you go ahead and draw our model for the battery. Maybe you don't have to draw all this or write all the words, because you already have this in your notes of the previous topic, but drawing the oppositely charged parallel plates and our uniform electric field between them, and our electron here, and the potential difference across them, and here the dashed line, which is the confines of the battery. But this is our model for the battery, the idea that this mechanism, the chemical reaction inside the battery, is doing work on these electrons, pushing them where they don't want to go, by all these other negative charges, giving them electric potential energy, right? And then the idea is we want to somehow release that energy. But that's what batteries do. They store energy. And now that we are firmly in the realm of batteries and circuits and things like that, we're going to rename delta V. We're going to rebrand it instead of potential difference as a voltage. In fact, this is the real reason why we use the capital V so incongruously to describe potential. Right? The real name comes from voltage. That's why it's measured in volts. Okay, so it all seems to make sense. So delta V is either potential difference or voltage. They mean the exact same thing. We're going to be drawing batteries a lot, and we don't want to keep drawing the oppositely charged parallel plates and all this stuff happening. So we instead have a series of symbols we're going to be using as we build up the ideas of circuits. And so this is going to be the symbol we use for the battery. It's all two parallel lines, the long line here representing the positive terminal, the short line representing the negative terminal, and then these lines coming off of them are wires, because the whole idea is the electron is held against its will, all this electric potential energy stored in there. Nothing's going to happen unless you provide an escape route. So we attach a wire here so the electrons can then leave and connect it all the way over to the other side. So we can actually watch as the electrons see the escape route, they leave the confines of the battery, they travel along the wire or some other conducting material, and then they come back in at the positive terminal, and now they're back inside the battery. Along the way, they've lost their electric potential energy to do whatever it is the battery is helping to do in the circuit. But now that it's back inside the battery, the chemical reaction says, oh, you're back, and it's going to do work on it again and push it back to the negative terminal where it doesn't want to be, so it restores the energy in it, and then it's free to leave and go round and round and round it goes. And now that's flowing. Now we have what's called current. I'm putting electric here in parentheses. It's implied. There are other types of currents, but, so when we say current, we mean electric current. So how do we define current? We define it as the rate of charge passing perpendicularly past a point in the conductor. A lot of alliteration there. The rate of charge. So not necessarily how quickly they're moving, but how much charge moves in a given amount of time, passing past some point in the conductor. So often the conductor is a wire, and wires are usually little cylinders, which I'm going to here magnify. Oh, sorry. First, let me just remind you that the word current is really just a synonym for electricity. We use them interchangeably. So let's draw a wire here as a sort of like a cylinder, a tube, sort of magnified here. Usually it's much thinner than that. And we'll identify some place along the wire, some cross-sectional area, and we're going to set up shop there and watch as charges flow across. Here I'm using capital Q not as the source charge like we had in the previous topic, more as an accumulation of charge. A whole bunch of charges bunched together to make some large chunk of charge passing by. The symbol for electric current, of course, will be a capital I. I say of course, but really there's no good reason for that. I'm not really sure why we use capital I for it. I'm not sure if there's some sort of historical reason, or maybe we just ran out of letters and we use capital I for something or other. So here we're going to use capital I for current. This is one of the reasons why early in the year I strongly advise you not to use capital I for impulse. That's why we use capital J for impulse. Alright, so here we're using capital I for current, and so it is the rate of charge with respect to time. Anytime we talk about a rate of anything, it's always with respect to time, and so it's going to be defined as capital delta Q over delta T. The amount of charge with respect to time, we can go ahead and box it in as our new equation. We'll do all of our usual stuff. Let's talk about scalar and vector. Okay, so the top is charge. Is that scalar or vector? Well, hopefully you remember that is a scalar quantity. I know it's a little confusing because I have an arrow here, but this arrow is really just representing the charges moving past that point in the conductor. So it's more like a velocity arrow, right? But charge itself is a scalar. It doesn't matter if it's positive or negative. That doesn't tell you anything about direction. It's just an amount of something. Time, vector, is scalar. Hopefully you remember that's scalar, and so current itself is a scalar quantity. How about the units? Well, we build it up from the equation. Charge is measured in coulombs. Time is measured in seconds. So of course it is coulombs per second. As we often do, we will rename the coulomb per second as capital A for ampere, named after a French physicist, André Ampère, although he was French, so it's probably more like ampere or something like that, but my French is not very good. So we're just going to call it ampere. Sometimes even abbreviated more as an amp. If you ever hear an amp, that is referring to an ampere, and 1 amp or ampere is the flow of 1 coulomb in a time of 1 second. we recall a whole coulomb is a tremendous amount of charge, and even 1 coulomb per second is a tremendous amount of charge. So 1 amp is actually a rather large current. We usually deal with much smaller currents in this class. We'll be dealing with milliamps and microamps and things like that, although certainly we'll be dealing with some larger ones as well, but that's not the usual. Okay, so let's go ahead and get started with the problem here in our problem set. Start with number 1, so go ahead and read it. Go ahead and solve it on your own. Pause the video as you do so, and then come back to see how I do it. Okay, so in the first part, we're going to take our only equation here, rearranging it for delta Q, the amount of charge passing by, so delta Q equals I delta T. Hopefully you saw that the current there is given in milliamps. You know, my advice is always just replace the metric prefix with its power of 10. Hopefully you also notice the time is given in units we can't use. If this is coulombs per second, the time must be in seconds as well. So we're just going to convert that into 4.20 times 10 to the -3 amps, and there's 120 seconds, so the units will correlate. And we should be getting 0.504 coulombs. Now, as I was just saying, a whole coulomb of charge is a tremendous amount of charge. It's very rare you'll see an individual object with a whole coulomb of charge, and half a coulomb is still a tremendous amount of charge, and that's not what's happening. What's actually happening is a whole bunch of objects are passing by that accumulate to make 0.504 coulombs in this amount of time. And so this second part here is we're going to find out how many protons would bunch together to make 0.504 coulombs. This should seem really familiar. We've done problems like this before where we split up the total amount of charge by, in this case, the elementary charge, the charge per proton, right? So we're going to take the 0.504 coulombs, divide by the elementary charge, which if you didn't know, we could always look it up. Although, after doing a whole bunch of problems in the previous topic, I would think more than likely this number is sort of stuck in your head as the charge on a proton. So you do the math, and we should be getting this amount, 3.15 times 10 to the 18th protons. Okay, how would you describe that amount, 10 to the 18th? Yeah. That's a lot, right? So what we're really imagining is inside this wire, there are just billions and billions and billions. There's actually a billion things flowing along. And again, I mentioned 4.2 milliamps. That's not a tremendous current. It's not a small current either. So let's say if we have like a battery powering a light bulb, maybe the current in this might be 4.2 milliamps. And so if this circuit were on for 2 minutes, you'd have to imagine just billions and billions of things flowing through the wire. In this case, we're tracking these protons, these tiny, tiny objects, just billions and billions and billions, so many protons. These protons flowing through the wire. And I keep referring to protons, and I'm doing that for a reason. Hopefully, every single time I say that, there's a big red flag going up in your mind saying, wait, Mr. Sadowski, something's very wrong here, because in our previous topic, when we were studying the atom and the structure of the atom, we know protons don't move. Where are protons? Oh, right, they're stuck inside the nuclei. They're bound together to the neutrons by those strong nuclear forces of attraction. They don't move. What does move? It's electrons, right? That's reality. Protons don't flow at all. That's wrong. Right. Yeah. Electrons are what flow, and yet we're not going to do that. No. Don't be silly. We're going to follow something called conventional current. And in conventional current, it tracks the flow of positive charge, in this case, protons. So we're going to pretend the protons are flowing, even though we know it's wrong. Now, why do we do such a thing? Well, it actually has a historical basis. Back in the day, when I say back in the day, I'm talking like the 1700s. I'm talking about Benjamin Franklin, one of the founders of our country, who was also a scientist. You know the story, lightning storm, kite, string, key, zzz, all that stuff, right? It's true. He was doing those things. He was experimenting with electricity, right? He was experimenting with current. And so he knew at the time there are two types of charge, positive and negative, and he figured out that current, electricity, was the flow of charge, but he had no idea about protons, electrons yet, hadn't been discovered. And so he didn't know which type of charge was flowing. And so I don't know if he was optimistic or he was just in a good mood that day, but for whatever reason, he decided that positive charges were the ones that flowed in electricity. And for decades, everyone said, yeah, sure, positive charge, why not? And then later that century, when they found out, actually it was about more than a century later, when they found out that wasn't true, that was actually the electrons that are the mobile charge inside the atoms. They're the ones that are flowing. Everyone said, well, we've been doing this positive charge flowing for this long. Why change now? And so they didn't. And we haven't. For hundreds of years, we've been tracking the flow of positive charge, even though we know in our heart of hearts it's wrong. But it's okay, because everyone does it. Everyone does it. And so if we all do it together, even if we're wrong, we must be right. That's the way it works, right? If we're all wrong together, we must be right. Okay. Now, there's another reason why it's okay if we're all doing the wrong thing. And it goes back to the idea of the model of the battery, right? So here we have our electron, which is works on it, it's held against its will by the negative terminal, and it's released here to go into the circuit, flowing around this way, and once it gets back in the battery does work on it again, and it flows round and round. But what if we change it to a proton, right? Let's say we have a proton in this electric field. which way does it want to go? Well, of course it wants to go this way, but we want to say that the reaction is doing work on it. Which way is the reaction pushing on it, giving it potential energy? Oh, this way, right? So we're going to change our idea. Now the protons are pushed to the positive terminal. That is where they would have a lot of potential energy. So we imagine these protons are held against their will by the positive terminal. And then when the escape route happens, these protons leave and they go through the circuit. They get back inside the battery. The battery says, oh, you're back, and pushes them right back to the positive terminal, releasing them into the circuit, letting them release their energy. And so we're now tracking the protons. Why is this okay? Well, we did say that it's the amount of charge per time. And if we're tracking electrons, but now we're tracking protons, remember, they have the exact same amount of charge, the elementary charge. And so if we accumulate them together, we're going to get the same clustering, the same total amount of charge in the amount of time, so we're going to get the same number. The other part of this is the fact that current itself is a scalar. Yes, we are showing which way the charges are moving, but even if we go back here and we say the protons flow around this way in a counterclockwise direction, whereas before the electrons traveled in a clockwise direction, who cares? Since current itself is a scalar, it doesn't really matter in which direction the charges flow, just that they're flowing. And so, the fact that current is a scalar and the fact that current is determined by the amount of charge means it doesn't really matter if we track the protons or the electrons. And so we will continue to do this. We are going to track the flow of protons even though we know it's wrong, because again, if we're all wrong together, we must be right. And I'm not setting up for any sort of failure. All physics students around the world learn conventional current. Everyone does it. Every single place does it together. And again, if we're all wrong together, we must be right everywhere, except in New York State. The curriculum for high school physics, which is called Regents Physics in New York State, is governed by a group of people called the Board of Regents, and together they decide on the curriculum for all the high school courses, and in their infinite wisdom, they've decided that Regents Physics students will learn reality, and they track the flow of electrons instead of protons, which of course is right, but it presents a few problems. See, I used to teach in New York State, and the course I was teaching was a mixture of this Regents Physics and AP Physics, and so in AP Physics we got to current first, and I taught them conventional currents. We tracked the flow of positive charge. Everything was good. They took their AP exam, which is great, but then they had to prepare for this statewide Regents Physics exam, and so we had to change over to electrons flowing, which totally confused them. And then, if these students went on to college and took more physics, they had to trade back to conventional current, because everyone else in the world does the flow of positive charge, protons. And so it was very, very confusing, but you know what? They dealt with it. Everywhere else in the world, we're fine. We're going to stick with conventional current, even though we know it's wrong. It's okay. So anytime we have a sustained flow of charge, we're going to track protons, even though we know it's wrong. It's okay. We'll be wrong together.